all along the course, and whenever we study control theory in general, we come across terms like systems, or control systems, or systems engineering. So maybe we should spend some time discussing what a system is. What a system is. And that's not an easy task, because a system is a quite general word, and not only in our everyday life, in which we use it quite often, but also in science. There are many subfields within science which give their own definition for the term. So here I won't try to give the best, the perfect definition for system, the infallible or flawless definition. I will simply write down the best I've been able to find, the most general, and from my point of view, the most satisfactory. So let me write it. Here it is. For us, a system is a set of elements interacting among themselves and with the environment. And I like this definition because it focuses on the two key aspects of a system. The fact that it incorporates or includes elements and relationships. So since a system is a set, we can draw their elements and a boundary. This is the boundary that tells what is inside the system and what is outside the system, which is the environment. This is the environment, and this is the system. And this is the boundary. And this resembles the thermodynamics definition for a system. For systems in thermodynamics, a system is just the part of the universe we're looking at. So it's quite similar to that. And as we said, there are relationships between the elements of the system and also with elements in the environment. There are interaction with the environment. So I think with this is enough to understand what a system is. So let's go with models. Again, let me write down the definition. A model is simply a system used to represent some other system. So the easiest example we can think of a model is the model of a building that architects use to, well, when they are designing or trying to sell a project, they build a model for the building. Well, this is obviously the system, and this is the model. Okay, but this is a model for a static system, not very interesting from our point of view. We care a lot about the evolution of the systems in time. So we use dynamic models. We work with the so-called dynamic systems. And besides, the model of a building is a physical model, and we'll be working with conceptual models, and in particular with mathematical models of dynamical systems. And those conceptual models of dynamical systems, must incorporate at least three key elements, three key points. The first one are parameters. That's the structure, the immutable properties of the system, the unchanging characteristics of the system. The second element or elements, the second group of elements are the variables, which represent the evolution, the how the system changes in time, and each variable, as we shall see, change or evolve within certain range. And finally, the third element are the laws, which define how variables change in time according to the previous state or value of the variables, and according also with the parameters. So these laws are the rules or the principles that the system follows in its evolution. So the purpose of these conceptual models is that what is observed in the model is coherent with what the actual system is showing. In terms of dynamical systems, that means that what the model produces must agree with the past of the system and with the future of the system. So the model must be able to predict to a certain extent the behavior of the system that is representing. This is predicting, that this is looking into the future. Well, the model must be able to do that. And if we have those two, then we have a good model, and in a way we could say that we are understanding the system, that we know the driving forces that work in the system. So from a certain point of view, having a model and understanding a system are the same thing. And that's actually the purpose of science. Science advances through the building of new models, better and better models for the observed phenomena. The scientific method, with all the observation, hypothesis, test, refinement, all that stuff, is an endless effort to achieve better models for all kinds of systems. In each subfield, they try to build better models, better and better models, which explain new phenomena. Well, there's a lot of interesting stuff here, a lot of nuances related to epistemology and philosophy of science, but unfortunately there's no room for that in the course, and I'm not the best person to go deep into that. But it is important to point out that when we face that we're always facing a trade-off when we choose a model for our system. It is true that science looks for the best model it can achieve, but in engineering and also in other areas involving decision making, we're not that committed to the actual truth. And that's because models have to be a good representation of reality, but they must also be tractable. So, as I said, models are useful to understand a system, but as we'll learn, we want them also to act on the system, to change the system according to our desires, to make the system behave as we want. And that is actually called to control it, to control the system. So for those two purposes we need models. And the richer a model becomes, the more information it conveys, the deeper it digs into the nature of the system, the more complicated it becomes to derive a control strategy. It's like making a decision after receiving tons of information. It is a good idea to be informed, but if you are overwhelmed by information, you'll probably end up making a poor decision. So we need to separate the wheat from the chaff. But that doesn't mean that we have to oversimplify things. We have to adapt our model to our purposes and choose the simplest model which still allows us to achieve our objectives. More complex objectives will demand more complex models, and as a consequence, more complex control. So let me illustrate this with a couple of examples. We can think of a box filled with a gas, and we can look at it like a physicist of the 19th century did, as full or filled with atoms, like small balls bouncing into each other and, well, moving around. Maybe if a chemist who was studying it, he could think of the interactions among the different atoms. This is a way we can look at the system. But if we are we are nuclear physicists, we could look deeper into the nature of each atom and look at the particles, the electrons around each atom, and all the quarks and all the other crazy stuff of nuclear physics. But also we can think in terms of engineering, and maybe we can think of the system as just a sort of continuous, which is perfectly defined, continuous matter, which is defined by properties like temperature. This could be 15 degrees Celsius, and I don't know, and pressure, and knowing the temperature and the pressure, we completely define the model, and maybe this is enough to work. And actually, that's actually the case. You can build a cylinder, piston systems with this very simple point of view. So as you see, there are different levels of detail here. The same is true, for example, in social science. We can think of society as people or agents interacting with other people, and maybe with I don't know, with companies. This is, well, it's not a very nice factory. Here it is. Maybe this is a worker of the factory, and they also go and buy some stuff in a shop. And there are also relations with institutions like courts. I don't know. Those are very complex interactions. But from the point of view of an economist, society can be seen as again a sort of continuous, defined by terms like inflation or unemployment or GDP, and there are certain actions, certain inputs which government can use to act upon the system. Things like like fiscal policy, or interest rates, or the public spending. And this will change, as we said, inflation, GDP, or unemployment. So the question would be again: is that level of detail enough to derive good control rules, good policies here, which are essentially control? Is this level enough to build an engine? Well, this is always a difficult question, but one that pays to ask ourselves about. But it is not the purpose of this course to choose the depth or the detail of the models we need. This corresponds to a modeling course. Our position will be: a model has been given, and what can I do with it? And most of the time we'll be able to derive control schemes, because they'll be pretty simple. If we were given more complex models, we would have to resort to advanced control, and that's actually the purpose of research in control theory, to derive better control techniques, achieving better performance for more complex problems. But remember that whether the actual implementation of the control scheme we have designed are successful or not will depend, among other things, on the validity of the chosen model. We have always to keep that fact in mind.